Hi, my name is Akshay and this is Half Sleeves. In this video, we will look at a solution to the problems with GANs. The main problem, as we discussed in the last video, is the lack of communication between the critic and the generator, or the two players who are playing the Minimax game. The solution to this problem explained in this video is based on the paper Generative Minimisation Networks. The link to that paper is in the description. From the first video, we know how the generator and the critic in a GAN are just playing a Minimax game and are trying to find the Minimax point. And we also know from the first video how they find the Minimax point. But to be honest, I didn't tell you the full picture in the first video about the Minimax point. So let's look at the same game again which was shown in the first video. Let's say we have two players, Boltzmann and Bohm. Boltzmann will be represented by BZ and Bohm by BM. They are playing a game. Boltzmann and Bohm both will select a number. The real number Boltzmann selects will be called XZ and the real number chosen by Bohm will be called YM. Now that both have selected a number, we will choose a function fxy. And both Boltzmann and Bohm will put their selected real numbers xz and ym in this function. And whatever is the value of z or fxy, Bohm will pay z amount to Boltzmann. We saw in the first video that this is exactly the game a GAN's critic and generator are playing, and they are trying to reach the Minimax point, where Bohm is the critic and Boltzmann is the generator. Xz and ym are the generator and critic's output. But you should remember that the outputs can also be considered as weights. Because when you have a neural network like this, here the inputs are A, B and C, and the output of this neural network is F. So when you have a neural network like this, the F or the output is a function of all the weights of that neural network. Further, this function x square minus y square is the loss function which the generator and the critic will be maximizing and minimizing. This loss function looks like a function of two variables, but in reality, this loss function is a really complicated function of thousands of variables, as the loss function depends on the output of the generator and the critic, which is x and y, or xz and ym. And xz and ym are functions of thousands of weights of the generator and the critic, as they are the output of the generator and the critic. So it is a function of all those weights. So the loss function is a function of n variables where n is a big number, and that is why this function can look like anything in the n-dimensional space. As far as the function x square minus y square is concerned, it looks like this, and it is a saddle graph function, which means it looks like a saddle. The thing which you know from the first video is that in a GAN, the critic and the generator, or Boltzmann and Bohm, are trying to find the Minimax point. Now the thing which I didn't tell you in the first video is the definition of the Minimax point, which they both are trying to reach. Let's look at the definition. The point where no player can improve its objective by just individual movement is called a Minimax point. Let's try to understand this definition step by step. First, our definition of Minimax point says that at Minimax point x0, y0, which is here, a player, which in our case is critic or Bohm. A player cannot improve its objective. Now, objective here means the objective of the player or the critic. The objective of the critic is to minimize the function, because Bohm or the critic wants to reduce his loss function or the loss of money which is being paid to the generator or Boltzmann. The last part says by individual movement. Well, movement means changing the output, and individual movement means changing its own individual output. This means that changing only critic or Bohm's own output, or it should only change the variable on which critic or Bohm itself has control. The critic or Bohm has only control over the value of y. So this line simply means that only change y variable and keep the x variable constant. So this line would mean that we would only minimize in y direction and keep the x constant. And keeping x constant would mean to keep the x coordinate same as the minimax point, which is at x0. We know that we are at minimax point. This is how the minimax point looks like on the graph. The function with constant x would look like this, and on the graph it would look like this black parabola. And we will minimize this function on y-axis. Now this term improve comes into play, which I didn't tell you about earlier. We know that the objective is to minimize the function on y-axis with x fixed at x0. Improving the objective means that if we are at y0, then we try to minimize the function and find a point on this black parabola which is even lower than y0. But as you can see graphically that if you try to minimize this black parabola, you will always reach this black point, which is the minimax point, and you would never go beyond or lower than this point, which means you can never improve your objective if you are at minimax point x0, y0. And the definition is correct. So as we saw, minimizing the black parabola is equivalent to reaching the minimax point x0, y0. But if we look at our original definition in red again, it says that at the minimax point, no player can improve its objective by just individual movement. The phrase no player is important because we have two players, Bohm and Boltzmann, and we have only seen that Bohm cannot improve its objective by just individual movement. So let's also see that for Boltzmann. So for the player here, we will put generator and change the objective here to maximizing this function over x with y fixed at y0. The function with y fixed at y0 and variable x looks like this. And on the graph, it looks like this black parabola. We want to maximize this black parabola. And if now you look at this black parabola and maximize it, you will reach that black point, which is the minimax point, and would never go beyond or above this black point. Which means you can never improve your objective if you are at minimax point x0, y0. And according to the definition, x0, y0 is the minimax point. So maximizing this black parabola is equivalent to reaching the minimax point x0, y0. So we just saw that both these conditions lead to the minimax point. This implies that both of them are equivalent. I'm going to leave the explanation of this onto you as we have already done these things in the first video. So this equality can be written as this, which itself can be written as this. And this equation can be used as a loss function to find the minimax point, meaning that we can train our network to minimize this loss function and find the weights xz and yz, such that those xz and yz satisfy this expression or formula. And this is also exactly what we were looking for. Remember that we were looking for a way to establish a communication between the critic and the generator, or the two players who are playing the minimax game. For example, if the critic minimizes the network, which is this part in this loss function, in such a way which hinders or stops the other network to do its task or its job, then the other network, which is generator, which is this part in our loss function, will adjust its own values to make this loss function 0. Which means that our generator was aware of what critic did and it changed its own actions to minimize this whole expression or whole loss function. And if you have seen the last video, you will know that this communication and the adjustment is exactly what we needed. When we minimize this loss function, it means that the goal is not just minimizing y and maximizing x, but now the goal is to minimize y and maximize x in such a way that this loss function is 0. So now if our network optimizes and changes x to reach the minimax point, it will have to also check the value of y and then make the appropriate changes to reach the minimax point. In other words, it means that now generator and the critic can no longer take independent strategies to find the minimax point, and their strategies will depend on what strategies the other network is taking to update its weights. So now our networks no longer only care about doing their task alone, but care for doing the task in such a way which serves the collective good of minimizing this loss function. Which also means that our generator is now aware of what critic does and it adjusts its own actions to minimize this whole expression. This adjustment is true for both critic and generator, so both critic and the generator adjust according to each other. Also, now our task is much more easier because now we don't maximize and minimize the loss function. Now we only minimize our loss function. So now, rather than competing with each other and working independently to minimize and maximize the loss function, our generator and critic will only minimize the loss function and work together. So our networks are no longer adversaries. Rather, they are partners and they work together to minimize the loss function. So this GAN can be renamed from generative adversarial networks to generative minimization networks. There's one more catch which is called realizability, about which I have not told you yet. Remember that in the first section of this video, which is named the game from the first video, I told you that the loss function is a function of n variables, where n is quite big and the graph of the loss function can look like anything. The obvious question after that statement is, what is the guarantee that all the loss function would be such saddle graph functions? Because we saw this property of reaching minimax only on saddle graph functions in our examples. A loss function can look like anything, as I said earlier, and not necessarily like a saddle. I will answer that question in later videos. But if you want, you can look for realizability in the paper in the description and find the answer yourself. In the next video, we will look at the Python code of how to implement this generative minimization network and converge to minimax point with that Python code.